color will it be today? Yellow.
Looks like it might have had an update. The sign's just.
Oh, I'm wondering, because the other instructor in here was talking about that she wasn't able to use this. It decided to reject her yesterday. And I'm wondering if she actually put in a ticket as opposed to just complaining for people today. All right, so we talked, especially in this example right here, where a magnetic field induces a current, which creates a magnetic field. We can be more specific, the fact that we have a changing magnetic flux, and we had that the EMF is equal to the negative change in the magnetic flux with respect to time. So suppose I have a coil, a solenoid, some like L with N coils. If I have current running through here, if it is at a steady current, so for right now, let's just assume a DC current, direct current from a battery. It's been plugged in, we've walked away, we come back, it's still going strong. My current flowing through it is constant. I have a magnetic flux that's going through the wire here, but it's a constant magnetic flux because my current is constant. Matter of fact, let's be more specific here. I know that the magnetic field strength is equal to mu in I. Double check that. Yep. And that's something that we derived when we introduced Ampere's law. The magnetic field is equal to the permittivity times the coil density times the current. And this is for a solenoid. But my magnetic field would be constant. If the current is constant, I'm assuming that whatever's inside, mu sub naught if there's just nothing in there. N is based upon the geometry of this, where N is equal to the number of coils divided by the length. Ooh, I think I do this probably 90% of the time. That L right there, I'm gonna change into a lowercase l. I recommend you do the same. I'm reserving capital L for something else that's coming up very soon. But what happens though, if I have this hooked up to a battery, so I got my battery here connected to a solenoid, what happens if the connection breaks? Somebody comes along and snips the wire.
Is it similar to what we did with the other circuits? Like some of the stuff stays the same and some of it doesn't? Like the
plate capacitors. Would it just?
So what you're thinking? Or were you just trying to figure out what he was thinking?
I'm trying to figure out a lot.
Will the magnetic field stay the same for the coils even though it doesn't have any more current running through it? Or I'm forgetting if when you got the battery, the voltage changed with the electric.
It sounds like you are trying to
Is that
parallel this with capacitors more than you should.
more than I should?
Yeah.
Okay.
All right, what happens if there's no battery connected to the coil?
No current is no current.
All right, no current, and if there's no current, what is about the magnetic field?
No magnetic.
All right. When there is current running through it, what do you know then?
There's a magnetic.
Okay. So if I have current running through it and suddenly we break the wire,
There's no current.
all right, so what happens? There's a transition there. We transition from having a magnetic field to not having a magnetic field.
Does it get smaller as the last of the current leaves the solenoid? Does it get smaller as
What gets smaller?
the magnetic field?
Well, I would think it would get smaller, yeah. Okay, so magnetic field gets smaller, so what about Faraday-Lentz's law? What does that tell us is gonna happen?
Electric flux is gonna go down. Or
Ooh.
magnetic flux.
Thank you. Yes, and therefore,
There's not gonna be any change in magnetic field.
that's a bit extreme. If there's no change to the magnetic field, how will the flux go down? The coil is not shrinking. All right, so we've established that the current goes to zero. Therefore, the magnetic field in the solenoid goes to zero. Therefore, there's a change in the magnetic flux. That's not zero. If there's a change in the magnetic flux, it's not zero. What does Faraday-Lentz's law tell us? This is Faraday-Lentz's law right here.
The EMF is gonna change.
Okay. I guess we can, the EMF, this induced EMF is not zero, more specifically. If the induced EMF, this is not the EMF from the battery, this is the EMF that's created because our flux is changing. If the induced EMF is not zero, what will be created? What does an EMF create in general? What is an EMF?
Isn't EMF electric motor force?
That's originally what it comes from, but what is it really? It's not a force.
Something to do with current.
Something to do with current. What is
Does
EMF?
it create a magnetic field?
Okay. You answered a different question that I had asked, but what is an EMF?
Electric motor current.
It is not a current. What are the units of an EMF? Well, that should be fun. Let's do a little current unit analysis here. So the units of the EMF will be the units of the magnetic flux divided by the units of time.
So Tesla meters per second?
So you say meters per second?
Tesla meters per second.
Tesla meters per second? No.
Or Tesla meters squared.
Okay, so this is the units of the magnetic field times the units of area over the units of time, which would be a Tesla meter squared per second. And now it's completely obvious, what is EMF?
The acceleration of, or the velocity. Yeah, velocity of magnetic fields.
All right, let's keep going. I know that F is equal to QVB in terms of units. from the formula F equals Q times V cross B. So that's a Newton is equal to a Coulomb meter per second Tesla. So therefore, a Tesla would be
A meter per second Newton. Or,
try again.
Coulomb meter per second.
You're solving for T. Maybe I've missed a few words.
Oh.
Everyone should
Newton
jump on
second
this.
per Coulomb meter.
Say it again.
Newton second per Coulomb meter.
Yeah. Newton second per Coulomb meter. So if we plug that in here, this becomes a Newton second per Coulomb meter times meter squared per second. Seconds cancel out. One of those meters cancel out. I'm left with a Newton meter per Coulomb. What's a Newton meter?
Like joule.
So that is a joule per Coulomb, which is
Voltage.
really close. Try again. Yeah.
Potential difference. Volt. Oh, volt.
Look for the volt. All right, so the units of the EMF are volts. What would you guess an EMF is?
Voltage.
Yes, EMF is a voltage. If I have a voltage that's not zero, what is it like? What does it want to make charges do?
Move.
Yeah, which means we have,
Non-zero current.
right. And if I have a current, what is that going to create?
Magnetic field.
All right, so as this collapses, as my magnetic flux goes to zero, it creates an EMF. That EMF will create a secondary current. I'll put a little 2 there to emphasize this is a secondary current, which creates a secondary magnetic field. So I had a magnetic field inside the coils already, but when the current starts dropping off, I create a secondary magnetic field. That secondary magnetic field is going to try to prevent the initial magnetic field from collapsing. The secondary magnetic field will try to bolster it back up. In a similar fashion, when I first connected, I'm reversing the process. My current goes from 0 to something. My magnetic field goes from 0 to something. My magnetic flux is not 0, which creates my magnetic flux changes, which means there's an EMF, which means there's a secondary current, which creates a secondary magnetic field, which tries to keep the magnetic field from increasing. The secondary magnetic field is trying to oppose the change in the magnetic flux. So if the magnetic flux is collapsing, it's going to try to bolster it back up. If the magnetic flux is increasing, it's going to try to suppress it. This type of setup here, what it is doing, it tries to prevent drastic change. Sort of a nuisance as you're trying to get current up to a certain point, but incredibly beneficial if there's a sudden power collapse. If you got a huge amount of current flowing through a coil and suddenly the power goes out, if this were not into effect, you have a very sudden change in the magnetic field, which would create a very large change in the electric field, and you potentially can get lightning. Or not necessarily visible, but you'd have electromagnetic radiation go shooting out. So you want to try to slow the collapse by putting something like this in there. This, and that's the symbol for it, is called an inductor.
What is this for? Or is it just a coil, like
It's a coil. Now,
on a diagram?
yeah. So in my circuit diagram, we have a power supply, resistor, capacitor, inductor. So resistor, capacitor, inductor.
Is there a fourth one that we're missing?
We will do an AC power supply. This is DC power supply. There are others, but these are the last one we will do will be an AC power supply.
Wait, how would an AC power supply look? Because if I imagine it looked like a capacitor.
AC power supply looks like that.
Okay.
The A in AC is alternating the current that's back and forth. All right, questions to hear?
Is there gonna be a situation where the magnetic flux is zero? Or does that just happen at the very beginning when nothing's happening?
Magnetic flux is zero if the area is zero or the magnetic field is zero.
Okay.
So,
And because in this situation we had one and it was trying to go away, we didn't have a zero magnetic flux, we had to change magnetic flux.
yes, the important thing here is the change in the magnetic flux, not whether the magnetic flux is zero or not. Which is one of the reasons why AC current can work so well, because we don't really care what the current is as much as the fact that it's changing.
So are we ever gonna have to do like parallel and series with inductors? Like adding them?
For DC, no. AC, it's fair game, but we haven't got that far yet. Although I don't think I've done it for AC. Not with 152. Oh, by the way. A second, based upon this, is equal to a Tesla meter squared per volt. Get one more unit of time. All right, so if I have my coil, and my EMF is equal to the change in the magnetic flux, and yeah, I kept the negative in there, the negative. What I want to look at here is that's the total change in the magnetic flux. I want to break it down to a single coil. So that's going to be equal to negative the number of coils times the change in the magnetic flux for one coil. So I'll put a little 1 right there over delta time. I know that the magnetic flux is B times A. B dot A. Now, for a solenoid, it's usually made of sturdy metal. It's a wire. It's not going to change its area in any significant way. So my area is constant. Also, in a classic situation like this, my coils are like this, so my area vector is pointing that way or that way. My magnetic field is going to be parallel to the length here. So what I'm getting towards is the magnetic field and the area vectors are parallel to each other. So that would be negative N delta BA over delta T. My area is constant, so it can factor out. And so the EMF is negative in A delta B over delta T. The magnetic field in the solenoid, delta mu, not capital N, little n, not L either, I over delta T. U sub naught is the permeability. I apologize if I called it permittivity earlier. It's the permeability of whatever's in the core of the solenoid or of the inductor. So it's a constant that's going to factor out. N is the coil density. That is specific to the geometry of that. So I'm going to bring that out. So I got negative N A mu little n delta I over delta T. Now this little n is the coil density. It's the number of coils per unit length. And so this is negative N A mu big N over L over delta T. And again, lowercase l times delta I. Wrote that bizarrely. All right. And so I'm left with negative N squared A mu over L times delta I over delta T. Do a quick check to make sure I didn't do something boneheaded, which apparently I seem to be doing today. This right here is specific to the geometry. We have the number of coils squared. U sub naught is what you have inside the core. A is the area, the cross-sectional area of the set of coils, not the wire itself, but the set of coils. And L is the length. This is specific to how this is created.